Hello and welcome to this lecture on multi-objective optimization. Before we start, let me remind you that this lecture requires some background in theory of optimization and genetic algorithms. So let's start. In real life, having multiple simultaneous objectives is quite common. For example, consider a business that wants to maximize productivity but at the same time wants to minimize the costs of running the business. Likewise, marketing companies want to maximize their audience but minimize their marketing budgets. And if you're into machine learning like myself, you wish to minimize the prediction errors of your predictive model, but at the same time also want to minimize the model complexity. But what is the challenge? The challenge is that often these objectives conflict. Doing better in one objective can sometimes worsen the performance in another. Therefore, multi-objective optimization is about getting the best trade-offs. But how do we even represent these trade-offs? This takes us to the question, how do we evaluate multiple objectives together? Suppose we own a small shop that has a limited capacity to sell some items. Suppose the shop sells D different kinds of items. Now, because the shop has a limited capacity, we have two objectives here. Number one, we want to maximize our profits. And number two, we want to do that while minimizing sales. Remember, our shop cannot sell too much. So our solution is a set of prices for these D items. So in this case, the solution is represented by set X, and this set X has D components, where these D components represent D different prices. So this X represents such a set of prices that achieves a right balance between the profitability and the sales. Now we are going to use an optimization method to find a really good solution that is a great set of prices. But to use an optimization method, we must first specify how the method will evaluate any solution that it comes up with. So our first attempt at formulating an evaluation scheme can be F1 minus F2. Together we call it FW. Now FW is also called the objective function or fitness function if you have a background in genetic algorithms. Notice we want to maximize FW, and FW will increase when F1 or profit increases and F2 or sales decrease. For example, if sales are 0 and profit is a very high number, a high value, then FW also has a very high value. But clearly you can't make a high profit or in fact any profit with 0 sales. Such a situation is infeasible. In other words, no set of prices will yield this situation. We can only find reasonable trade-offs between our two objectives. Notice with FW, the importance of both F1 and F2 is equal because their coefficients are 1. Instead, we may decide that one objective is more important than the other. For example, we decide that making a high profit is more important than decreasing sales. In that case, we can attach weights to each objective. So our new objective function or fitness function FW is now W1 times F1 minus W2 times F2, where W1 and W2 are simply fractions that sum to 1. Or we can say they're percentages. So if the profit is more important to us, maybe we can set W1 equals 0.6 or 60% and W2 to 0.4 or 40%. Now another thing that we must keep in mind is that a maximization problem can be easily inverted to make a minimization problem. For example, maximizing FW is the same as minimizing the negative FW. In fact, it is quite common to show optimization objective functions as minimization problems. Now, if we want to implement such a weighted objective function in an optimization method like a genetic algorithm, then we simply have to write a new fitness function that weights different objectives as shown in the slide. Regardless of whether it is a maximization or a minimization problem, weighting multiple objectives is subjective. Setting good weights either requires prior problem knowledge or experimentation. Experimentation means that we set different combinations of weights and then check which combination generates the best results. An issue with weights is that different objectives may have different scales. For example, profit may be in millions while sales can be in hundreds. This can happen if you're selling expensive items like helicopters or jewels. Clearly, the impact of maximizing profit in this case will be much more than minimizing sales. Therefore, the optimization method can easily focus at just one objective at the cost of another. The optimization process thus effectively reduces to a single objective optimization. One solution to this can be normalizing the objectives, so the scales of values of all the objectives are identical. So we can try different normalization formulas. For instance, those formulas that can ensure that the values of both f1 and f2 range between the same set of values, that is between 0 and 1. We can try this for our problems and see if it works for our problem. However, sometimes it is still easier to find better values for one objective, and if that is so, the optimization process ignores the more difficult objective. For example, suppose one objective behaves like the chart on the top, and we can clearly see that a simple hill climbing approach can find the best solution for this objective. However, finding the best value for the second objective function at the bottom may be difficult because this objective function is noisy. So finding good values may be hard for the optimization method. So in this case, there's a risk that the optimization method, such as genetic algorithms, may only optimize the top objective. In certain situations, we can prioritize our objectives. If this is so, the optimization method can use what is called a lexicographic approach when choosing between two individuals or two different solutions. If we are using a standard genetic algorithm, the GA can use a lexicographic selection method when selecting parents for the next generations. The process, in fact, is quite simple. Suppose we have two individuals or two solutions, X and Y, and we want to compare which is better. So first we compare the two individuals based on the high priority objective. So in this case, the highest priority objective is F1. Therefore, if F1X is better than F1Y, then we prefer X. Sometimes small differences are not enough, so we check if F1X is significantly better than F1Y. For example, we check if there's at least some minimum percentage difference. If there is no difference or no significant difference between F1X and F1Y, then we move to the next objective on the priority list. And then again we compare whether F2X is better than F2Y or whether it is significantly better. This way we keep checking for all the objectives down the priority list until we can decide which of X and Y is better. If the ties persist all the way, we can either choose randomly. Alternatively, if originally we were looking for significant differences and couldn't find any, then we can go back to our highest priority objective and simply pick the numerically superior individual at the highest priority objective. So we can try various approaches. The lexicographic approach is useful in that it does not suffer from issues of scales because it compares values for each objectives separately. It is also simpler to use than some sophisticated approaches to be discussed later. However, the downside is that the priorities must make sense based on the problem domain. Also, the search process or the optimization process is primarily led by the highest priority objective. And if there are not many ties at the highest priority level, the lower level objectives will not have much say. So essentially, utilizing lexicographic approach requires good problem insight, and as a user of optimization, you must sit down with the problem expert to carefully decide how to implement the lexicographic approach. And in case you want to, you were wondering, where to use lexicographic approach, for instance, in a method such as genetic algorithm, if you want to use a lexicographic approach, you must design a new selection method that your optimization procedure, such as a genetic algorithm, can use when selecting parents for the next generation. An example of lexicographic selection is used in machine learning methods such as genetic programming or grammatical evolution. Even though you may not have seen these methods before, suffice it to say that they can be used to generate populations of predictive models. However, these models are often large, bloated, and complex mathematical expressions. Instead, ideally, we want a predictive model that is both accurate and yet simple to describe. Therefore, controlling this bloat is a major concern for practitioners of genetic programming. So one approach to keeping bloat under check is what is called the lexicographic parsimony pressure that is implemented using tournament selection in genetic programming. Therefore, when comparing two models in genetic programming, first we compare the predictive accuracy of the two models, and if there's a difference in accuracies, we select the more accurate model. However, if the accuracy is the same or not significantly different, then we move on to the secondary objective and pick the simpler model, or the model with a smaller sized expression. As mentioned earlier, there will only ever be any pressure to produce simpler models if the comparisons over the first objective produce ties. For example, if the accuracy values are integer values that vary only between a small range, then we shall have many models with identical accuracies. This will allow the lexicographic method to bring in the secondary objective, that is model simplicity. If the accuracy can be a real valued number over an infinite range, then the chances of finding a tie on accuracy are very small. For instance, one model could have an accuracy of 0.511, whereas the other could have an accuracy of 0.5111. So for all practical purposes, maybe the two models are pretty much the same. But numerically, there is a difference in their accuracy. So the more accurate model will always win the comparison of the first objective. So in this case, we shall not reach the secondary comparison. So because we, with such a grading scheme, an accuracy grading scheme, because we rarely reach the second comparison, as a result, the optimization process keeps producing only small improvements in accuracy while completely ignoring the model complexity. So as a result, the lexicographic approach in certain implementations of genetic programming does not work to induce parsimony pressure. So as a result, we have to be careful, in implementing the lexicographic method. Sometimes we only need to optimize one objective, whereas the values of other objectives should not exceed or fall below a threshold, which is represented by this Greek symbol epsilon, this funny looking E symbol here. Therefore, our fitness function tries to optimize only one objective that we call f, or f of x in this case. However, each time the fitness function is called, it also checks whether the values of the other objectives stay within the prescribed limits. So for example, g1x must be less than or equal to 0, and g2x must at least be equal to 1. Here 0 and 1 are the two respective limits, namely represented by epsilon 1 and epsilon 2. Essentially, g1 and g2 act as constraints, and this is why the reason is that there is no pressure, for instance, to bring g1 much below 0 or g2 much above 1. Notice we are only optimizing f of x. Okay. For g1x and g2x, all that matters is that they obey these constraints that we have mentioned here. So the objectives g1 and g2 effectively act just as constraints. Now, if we are to implement epsilon constraint method in a genetic algorithm, we have to implement it as a fitness function. Let us discuss that in some detail. In the fitness function, first of all, we check if any of the constraints are not met. If so, we assign a suitable penalty. For example, we can simply return the worst fitness value instead of proceeding any further with the fitness function. However, if none of the constraints are violated, then we evaluate the main objective f of x and return its value as the fitness value. Notice, however, in this case, only f of x is optimized as an objective, and the other objectives are simply constrained within some limits. So therefore, this approach does not guarantee that all the objectives will be optimized together. We now move to what is perhaps the most common approach to multi-objective optimization, and it is the so-called Pareto approach. This approach simply treats each solution as a trade-off. So a solution S1 is better than another solution S2 if it is at least equal to S2 in all the objectives, and S1 is strictly better than S2 in at least one objective. If the above two conditions hold, then we say that S1 dominates S2. Now there are different notations that can be used to indicate whether S1 dominates S2. These are shown on this slide. Whichever you choose, just explicitly define your notation first and then stay consistent with it. Let us now visually see how these, how to plot these trade-offs in a two-objective space. So here's a business that wants to minimize its loss of productivity, but at the same time wants to minimize the cost of running the business as well. Let us now plot different business strategies as dots on a two-dimensional plane and see the trade-offs they offer. Although what is the best trade-off will be decided by the business, but here we consider those trade-offs the best that cannot be dominated by any other feasible solution. Together, these solutions that are not dominated by any other solutions constitute what we call a Pareto front as well. So let's plot some sample solutions represented by these black dots. Notice none of these solutions dominates any other point. Let us confirm by comparing solution 1 with solution 2. Notice solution 2 is better than solution 1 on the y-axis, that is the loss of productivity axis. But then solution 1 is better than solution 2 along the x-axis. Therefore, neither of solutions 1 and 2 dominates each other, or you can say none of them Pareto dominates each other. You can pause here and verify yourself that in fact none of the black points can dominate any other black point. In fact, there is no feasible solution that can dominate any of these solutions represented by the black points. When we identify such a set of solutions that cannot be dominated by any other feasible solution, we call such a set as the Pareto front. Now you may say, well, a solution that costs 0 and reduces the loss of productivity to 0 as well will dominate all these black points. Well, that is true, but that is not feasible. In fact, such a solution and many other solutions will remain infeasible for various practical reasons. Such infeasible solutions are represented by the blue region. Now there can be some solutions that are strictly worse than these black dots. So they are represented by these greenish dots here. So because they are strictly worse than these black dots, we can say all the black dots dominate these solutions. Still, there are some other solutions that are dominated by some solutions, but not by the others. To differentiate between these different types of solutions, we shall shortly introduce what is called Pareto ranking. But before we move to Pareto ranking, let's refresh ourselves on the concept of Pareto front and non-dominance. When we have a set of solutions such that none of them is mutually dominated by any other solution, they are called the set of non-dominated solutions. And together, they make the Pareto front or the set of Pareto optimal solutions. All these non-dominated solutions are better than each other on one objective or the other. The concept of Pareto fronts is attributed to Wilfredo Pareto, who was an Italian engineer and an economist, and used the concepts in economics and income distribution. In fact, Pareto fronts are quite commonly used in economics literature, and they're also called as indifference curves. Before we proceed any further, notice that the exact shape and distribution of the Pareto front varies from one problem to another. Likewise, the infeasible regions also vary. Why do you think that happens? Well, the answer is that for each problem, the set of practical solutions can vary, and hence the collection of the best possible trade-offs varies naturally as well. Before proceeding further, let me introduce the concept of Pareto ranking that I mentioned a couple of slides earlier. So notice all the non-dominated solutions, which are represented by this black line here. These are non-dominated solutions because there's no solution that can dominate the solutions that are connected by this black line. So because nothing dominates these solutions, they are given the rank 0. This is the best rank. The solutions that are only dominated by rank 0 solutions and nobody else are given rank 1. Notice that not all the solutions on rank 1 are dominated by all the solutions at rank 0. Okay? But there are some rank 0 solutions that dominate every one of these rank 1 solutions. Maybe this one is dominated by this solution, and this one here is dominated by this solution, so on and so forth. Likewise, there are solutions that are in turn dominated by rank 1 solutions, and they are given a rank 2. And this process goes on. Now here's an exercise for you to pause and reflect. Pause here and identify the regions of dominance for 2 sample solutions, that is the blue solution here and the hollow solution here. Both these solutions are at rank 0. I want you to figure out how the region of dominance looks like in a 2-objective space. It is critical that you pause, draw your own figures something like the one here. It doesn't matter if your Pareto ranks are not exactly the same as those appear on this slide. Just draw your Pareto ranks and then figure these regions out, the regions of dominance. I want to see, first draw which solutions do these solutions dominate, and eventually can you put an overall shape around the region of dominance. Okay, so here's the solution. Each solution dominates the rectangular regions on its top and right sides. If you didn't pause and work it out, I suggest you do so that this makes perfect sense to you. Notice the regions are on the top right because we are minimizing both objectives. And the reason that the shaped region is rectangular is because we only have two objectives. If instead, say, we had three objectives, the rectangle would look like a cuboid extending out of the screen towards you. If instead we were maximizing the two objectives, how will the region of dominance look like? I will let you figure that out. Now, the purpose of Pareto multi-objective optimization, instead of single objective optimization method like a simple generic algorithm, is to return not just a single solution, but a set of solutions on the Pareto front. This set of solutions is called the Pareto optimal set. The purpose of finding this Pareto optimal set is to present the end user, that is the business user, with a diverse set of trade-offs. The user can then pick the best trade-off as suitable. Notice there are no ad hoc weights in Pareto optimization. However, the flip side is that Pareto optimization algorithms are far more complex than single objective optimization methods. And I'm going to show you the names of two most popular Pareto optimization methods. These are called apologies for skipping ahead. Yeah, so now we are back to where we were. So the names of the two most popular methods of Pareto optimization are the non-dominated sorting genetic algorithm 2, and the other one is called SPIA-II, which stands for Strength Pareto Evolutionary Algorithm 2. Now, the purpose of a Pareto optimization algorithm is to Pareto rank the entire population of solutions according to their dominance scores. Now, in this case, the fitness of each individual is its Pareto rank. So why do we Pareto rank the individuals? It is to give everybody, every individual or every solution a Pareto rank. However, when the two solutions have the same rank, some other tie-breaking methods can apply as well. These tie-breaking methods are unique to each Pareto optimization method. However, notice that Pareto ranking an entire population of solutions is an expensive process, because notice there are so many solutions. All these solutions have to be compared against all the other solutions into the population. And that the comparison doesn't happen just once, it happens a number of times because there are so many objectives involved, at least two objectives. Maybe there are three objectives, maybe four objectives. So if there are n population members, so each of those n has to be compared against every other member, and then those comparisons have to repeat across a number of objectives. So as a result, the process is a complicated one. However, Pareto ranking a population that has been expensive this expense was overcome by NSGA-II in a much better fashion than was done by any of the previous Pareto optimization algorithms. This is why NSGA-II became hugely popular, because it did this Pareto ranking very efficiently. Details of the Pareto ranking process can be found in the original paper that introduced the NSGA-II method. So while you can find the details of NSGA-II in the original paper, here we shall discuss how the selection process, the parent selection process, works in NSGA-II. NSGA-II, despite using Pareto optimization, also uses a lexicographic approach to compare two solutions. First of all, NSGA-II compares the Pareto ranks of the two solutions. So there's a solution I and there's solution J. If the rank of solution I is lower than the rank of the solution J, then I is the winner. However, if the ranks are identical, then NSGA-II breaks the tie by finding what it calls a crowding distance. The purpose of finding this crowding distance is to figure out which of these two solutions is more different. Notice both the solutions belong to the same rank, so they belong to the same Pareto front. Okay, so now we have to figure out which of these two solutions is more unique. Okay, so for that purpose, the NSGA-II uses what it calls a crowding distance. To measure this crowded distance, NSGA-II draws a cuboid. In this case, because it is only two objectives, so the cuboid is replaced by a rectangle. So it draws a rectangle around the solution of interest in the multi-objective space. So let us consider this solution I. The endpoints of this rectangle or cuboid actually reflect the two nearest solutions to I. Now, you can imagine, the bigger this rectangle is, the more is the distance between I and its two nearest neighbors. And if certain solution I is further away from its nearest neighbors, it means it is quite different to its neighbors. And that is what this crowding distance meant to show. So NSGA-II computes this crowding distance for each of the two solutions. So if it is comparing this solution I with another solution J, it will first compute this crowding distance for I, and then it will also compute the crowding distance for J. And then whichever has a greater crowding distance wins out. So in summary, we have introduced the notion of multi-objective optimization in today's lecture and discussed three different approaches, that is, weighted objectives, epsilon constraint method, and Pareto optimization. We discussed the strengths and weaknesses of each method. For more information on Pareto optimization, consider, for example, the original paper introducing NSGA-II, that is a fast and elitist multi-objective genetic algorithm, NSGA-II by Deb et al., that came out in year 2002. To see the implementation of NSGA-II in R, download and install the package MCO and look up the function called NSGA-II. If you have any comments or questions, please leave them in the comments section below. Thank you for watching.